We're now going to discuss colligative properties, which depend only on the number of particles in solution. So these properties don't depend at all on the chemical identity of the particles, only on how many the particles are dissolved in solution. So the concentration. These properties are the boiling point elevation, freezing point depression, vapor pressure lowering, which is tied to the boiling point elevation, and osmosis. Let's first look at vapor pressure lowering, which is expressed in Raoult's law. This is going to say that the vapor pressure of a solution is going to be equal to the mole fraction of the solvent times the vapor pressure of the solvent if it was pure. The second thing we'll look at is boiling point elevation. With boiling point elevation, we see that the change in temperature of the boiling point is going to be equal to something known as the boiling point elevation constant, which is specific for a particular liquid, times the molality of the solute in the solution. The next thing we'll look at is the freezing point depression, which looks a lot like boiling point elevation. The freezing point depression looks like this. The change in temperature of the freezing point is going to be equal to the freezing point depression constant, which again depends upon the solvent, times the molality of the solution. These look identical except for, the subscripts here, but we should recognize that with freezing point depression, this constant here is negative, and this negative tells us that the freezing temperature will drop. In the case of the boiling point, this is a positive constant, which tells us that the boiling point is going to increase. And finally, we'll look at osmosis. And in terms of osmosis, there's a pressure that's seen, and that pressure is signified as the Greek symbol pi. And the osmotic pressure is going to be equal to the concentration of the solution times the gas constant times the temperature. We're going to do a problem with all four of these. The first problem we're going to do says, suppose 651 grams of ethylene glycol, which has this molecular formula, is dissolved in 150 kilograms of water. So this is going to be our solute. This is our solvent. What's the vapor pressure of the water over the resulting solution at 90 Celsius? And they give us the vapor pressure of pure water at 90 Celsius as 528 millimeters of mercury. This is a problem that deals with Raoult's law, vapor pressure lowering. We're going to find that the vapor pressure of the resulting solution is going to be less than the vapor pressure of the pure water itself. When we use Raoult's law, we're going to remember we're looking for the vapor pressure of the solution. To find that, we'll take the mole fraction of the solvent in the solution, and we'll multiply that by the vapor pressure of the pure solvent. So let's write this equation down that we're going to use. We want to know the vapor pressure of the solution, and that's going to be the mole fraction of the solvent times the vapor pressure of the pure solvent, which in this case is water, and is given to us right here. So we're just going to plug this in here. The trick to this is going to be finding the mole fraction of the solvent. What is the mole fraction of the solvent? Well, the solvent's water. So we're going to need the moles of water relative to the total moles of the solution. What's in the solution? Well, in the solution, we have our ethylene glycol, and we have, of course, water. So we're going to need to find some moles here. We're given the mass of ethylene glycol, so we can use its molar mass to find the moles. Let's do that first. 651 grams of ethylene glycol. How many grams are in a mole for ethylene glycol? Well, let's see. I've got 2 carbons times 12 grams per mole. I can figure that out by looking at the periodic table. We're going to add to that for hydrogen. We have 6 of those times 1 gram per mole each. And then for oxygen, we have 2 of those at 16 grams per mole each. That's 32 grams per mole. We add all this up, and we get 62 grams of ethylene glycol is a mole. So we take 651, we're going to divide that by 62, and we get 10.5 moles of ethylene glycol. Now we'll do the same thing with water. How much water is in the solution? 150 kilograms, which you better recognize, that's 150,000 grams. So we're going to take 150,000 grams of water. That's a lot. And we're going to end up dividing that by 18 grams of water in a mole of water. So we take 150,000, divide that by 18, and we get 8,333. So our mole fraction of water is going to be 8,333 divided by 10.5 plus 8,333. So we'll do the numerator first, plus 10.5, so that's the the denominator. The denominator is 8344, rounding up. We're going to take this divided by this, so I can just take this number, which is the denominator. I'm going to take the inverse of it, so I'm just going to flip it. And then I'll multiply that by 8333. The mole fraction of water in the solution is going to be 0.9987. So that's our mole fraction of our solvent is 0.9987. And we'll need to multiply that by vapor pressure of the pure water, which is 525.8 millimeters of mercury. So these two numbers will be multiplied together. We figured out the mole fraction of the solvent, which is the water. We have the vapor pressure of the solvent. We're going to multiply those two together. 525.8, 525.1. So we see that the addition of the roughly 650 grams of ethylene glycol to 150 kilograms of water lowered the vapor pressure from 525.8 millimeters of mercury to 525.1 millimeters of mercury. In this problem, we see we have a solution prepared from 1 1/4 grams of oil of wintergreen, and that's dissolved in 9 grams of benzene. The solution has a boiling point of 80.31 degrees Celsius. We're supposed to determine the molar mass of the compound of oil of wintergreen. We're given the normal boiling point of benzene as 80.1 degrees Celsius, and we're given this should be the KBP, the boiling point elevation constant, as a positive 2.53 degrees C per mole for benzene. So we see this is a boiling point elevation problem where we have a change in the boiling point that goes from 80.1 to 80.3 degrees C. We're given the boiling point elevation constant, and it looks like we're going to need to figure out the molality. I know we're looking for the molar mass, and from that molar mass, from the molality, we'll be able to figure out the molar mass. Here's how. The equation is the change in temperature of the boiling point, which is going to be 80.31 minus 80.1, so it's 0.21 degrees C. That's going to be equal to our boiling point elevation constant, which is given here, times the molality. Now I'm going to write the molality like this. That's the moles of our solute divided by our kilograms of solvent. That's the definition of molality. We don't know the moles of solute, but we do know the kilograms of solvent. Of course, we know this and we know this. We know everything but the moles of the solute. We're looking for the molar mass, which is the grams per mole of the solute. Notice we have the grams of the solute, and we can use this, this, and this to find the moles of the solute. So doing a little bit of algebra, we're going to divide both sides of this equation by kBp. And that gives us the change in temperature of the boiling point divided by the boiling point elevation constant. That's going to be equal to the moles of solute times the divided by the kilograms of solvent. Of course, this is what we want. We want to find this so that we can get to the molar mass. So let's multiply both sides of this by kilograms of solvent. We've got our equation here. We'll see that we take the kilograms of the solvent, which we know, 0.099 kilograms of benzene. We know the change in temperature of the boiling point, 80.31 minus 80.1. We know what that is. And we know the boiling point elevation constant. So store everything in here so we can find the moles of our solute. So our kilogram of solvent, that's 0.099 kilograms. Right there. We're going to multiply that by the change in temperature of the boiling point, which is 80.31 minus 80.1. That's 0.21 degrees C. And we're going to divide that by the boiling point elevation constant, which is a positive 2.53 degrees C per molal. Well, what is this? Well, that's going to be degree C cancels degree C. But this is an issue here. I got a kilogram on the numerator and a per molal on the denominator. Well, what is that? Well, a molal is a mole of solute per kilogram. So that means this unit here looks like it's going to be a mole to the -1 on the denominator times a kilogram on the denominator. Let me do this a different way. We've got an inverse molal on the denominator. Anything that's on the inverse, that's an inverse on the denominator, we can put on the numerator like that. And we know that the units of molality are moles per kilogram. So an inverse molal on the denominator is like a mole per kilogram on the numerator. There are kilograms cancel. We end up with units of moles. That's a long way to get there, but we still get there. Now we're just left to do the arithmetic. 0.099 times 0.21 divided by 2.53. 0.0082 moles is our moles of solute. Remember, we want the molar mass, and we have the grams of solute. So we're going to take our grams of our solute divided by 0.0082 moles, and then we should be home free. 1.25 divided by 0.0082, and we get 152 grams per mole. All right, let's try this problem. If 1,525 grams of ethylene glycol, C2H6O2, is added to 3 kilograms of water, will the resulting solution freeze at -10 Celsius? For water, the freezing point depression constant is -1.86 degrees Celsius per molal. What we want to do here is we want to find how much the water, how much the temperature of the water, the freezing temperature of the water is going to drop upon addition of ethylene glycol to the water. So we're going to use this equation here. The change in temperature of the freezing point in the water will be the freezing point depression constant for water times the molality of the solution. So we'll write this here. We want to know the change in temperature of the freezing point. That's going to be equal to the freezing point depression constant for water times the molality of the water. Excuse me, the molality of the solution that results. Well, that's going to be, I'm going to write it out like this, KFP. The molality, let's recall, that's going to be the moles of the solute, which is ethylene glycol, for every kilogram of solution, of solvent, which is the water. We know it's here, 3 kilograms. Okay, I know I can plug this in here for the freezing point depression constant. I know I can throw in the 3 kilograms for the kilograms of the solvent. I just need to find the moles of ethylene glycol, and then we'll be able to calculate the change in temperature of the freezing point. So I got to figure out moles of ethylene glycol. I have grams, so we need to know the molar mass. So let's see, I have 2 carbons. It's going to be 2 times 12 grams per mole. Find that on the periodic table. That'll be 24. For hydrogen, we have 6 hydrogens. It's going to be 6 times 1 gram per mole for a total of 6. And then we have 2 oxygens. So that'll be 2 times 16 for a total of 32. If we add that up, that's going to be 62 grams in a mole. So I take my 1525 grams and we're going to multiply that by, well, actually divide by 62 grams of ethylene glycol and 1 mole of ethylene glycol. So let's see, we have 1525, divide that by 62, we have 24.6 moles of ethylene glycol. So now we can plug everything in here. My freezing point depression constant is -1.86 degrees C for every molal. And then this, that's per molal, moles of ethylene glycol is 24.6 moles for every 3 kilograms of the water. Moles of solute per kilogram of solvent, that's molality. So this molality cancels the inverse molality. And now we're going to be left with our degrees Celsius, the drop in temperature of the freezing point of water. We calculate that, 1.86, we're going to make it negative. We're going to multiply that by 24.6, and then we're going to divide that result by 3. So the change in temperature of the freezing point will be -15.3, rounding down, degrees Celsius. So the freezing temperature of this solution will be -15. That's how low we'll need to get the temperature to freeze this solution. So the resulting solution won't freeze at -10 Celsius because it's not cold enough. It needs to drop below -15.3 in order to freeze. And remember, for the change in temperature of this freezing point, we're going to need to remember that the freezing temperature of water is 0. So the delta T, it's going to drop 15.3 degrees C. And with water, it's easy because water's freezing temperature is 0 degrees Celsius. If it drops 15.3 degrees C, that'll give us a freezing temperature of minus 15.3 degrees Celsius. And we see that the addition of this much ethylene glycol, this much ethylene glycol to 3 kilograms of water will be sufficient to keep the water from freezing if it's cooled to negative 10. In fact, it'll keep it from freezing all the way down to minus 15.3 Celsius. Okay, here's our last problem dealing with colligative properties. In this case, we see we have 1.4 grams of a polymer, and it's dissolved in enough water to make exactly 100 milliliters of solution. The resulting solution exerts an osmotic pressure that's 1.86 millimeters of mercury at 25 Celsius. And we need to figure out what's the molar mass of the polymer. Now we're clearly going to be using the osmotic pressure equation, which is this here. The osmotic pressure is the concentration of the solution. This would be in units of molarity, by the way, times the gas constant times the temperature. So let's see what we know here. Let's see. We've got the osmotic pressure is the concentration of the solution times the gas constant times the temperature. Let's remind ourselves that the gas constant is 0.0821 liter atmosphere per mole per Kelvin. So we know we're going to need our temperature in Kelvin. We know we're going to need our pressure in atmospheres, and our concentration is going to need units of moles and liters. Remember, moles per liter, that's molarity. How's this going to help us? Because we're looking for a molar mass of the polymer. Well, let me expand this a little bit. All right, so my osmotic pressure, that's going to be my concentration in units of moles per liter, correct? Times the gas constant times the temperature. Well, I know my liters of solution. I'm going to know the temperature. So I know this, of course I know the gas constant, and they gave us the osmotic pressure. So I know this, I know this, I know this, and I know this. The only thing I don't know is moles, and we're looking for the molar mass, which is the grams per mole. The only thing I'm missing, the only piece of the puzzle I'm missing is the moles. So what we're going to do is we're going to try to find the moles given all these. So I'll divide both sides of this equation by RT. And if I do that, I get pi, the osmotic pressure, over RT is my moles per volume. Multiply both sides by volume, and I get that my moles, which is what I'm looking for because I want my grams per mole, that's going to be equal to the osmotic pressure times the volume divided by R divided by T. And as long as we have everything in the appropriate units, we're going to be in good shape. Well, my pressure's not in the right units. I need those in atmospheres. I have those in millimeters of mercury. And we know how to fix that. We're going to take our 1.86 millimeters of mercury, and we're going to recognize that there are 760 millimeters of mercury in 1 atmosphere. 1.86 divided by 760, that's pretty small, 0.00245. Rounding up. So my pressure is going to be 0.00245 atmospheres. My liters, my volume, that's just going to be 0.1 liters, right? 100 mils is 0.1 liters, so my volume is 0.1 liters. My gas constant I've got here, and my temperature, I'm going to add 273 to this, 273 and 25 is 298 Kelvin. I think I got everything. So my moles is going to be 0.00245 atmospheres. We are going to multiply that by the volume, which is 1/10 of a liter. We're also going to divide that by 0.0821 liter atmosphere for every mole, for every Kelvin. And we're also going to divide by 298 Kelvin. Atmosphere on the numerator cancels atmosphere on the denominator. Liter on the numerator cancels liter on the denominator. On the denominator, we have both a Kelvin and an inverse Kelvin that'll cancel each other. We have an inverse mole on the denominator, which is a mole, and that's the unit we're looking for. So we know we've done this correctly. Now all we need to do is the arithmetic. So I take 0.00245, multiply that by 0.1. We're going to divide this by 0.0821, and we're also going to divide this by 298. That's not a whole lot of moles. What is that? 1, 2, 3, 4, 5. So the number of moles is 1.0 times 10 to the negative fifth. Make sure I did that right. 1, 2, 3, 4, 5. Yep, that's right. So the molar mass, which is what we're looking for, is going to be the grams per mole. So the molar mass is going to be 1.40 grams divided by 1.0 times 10 to the negative fifth moles. Almost home free. 1.4 divided by 1 times 10 to the negative fifth. So my molar mass is going to be 140,000 grams per mole. Now that looks really big, and it is, but we're going to need to remember that polymers are very long-chained carbon atoms, molecules made of carbon, and so a molar mass of this size is not too outlandish for a substance that's, a polymer substance.